Today we're going to talk about colligative properties, and colligative properties are properties that change when you have something dissolved in your solvent. Okay, so there are lots of colligative properties, but we're just going to focus on two of them. The first one is boiling point. So when you have a substance dissolved in your solvent, so the solvent we're going to use today is just water, which is the one you'll most commonly encounter and the one we're going to use in the lab as well. Right? So we know that when water is in the liquid form, it is forming some interactions, right? And those interactions are a combination of dispersion forces, dipole-dipole interactions, and hydrogen bonding. Okay, the strongest ones that are there are going to be the hydrogen bonds, so that's the ones we usually focus on. All right, if we dissolve a salt in our water, like sodium chloride, which has Na plus ions and Cl minus ions, then you can get ion dipole interactions with the water. So you can see that the sodium ion here is interacting with the negative end of the waters with the oxygens, and the chlorides are going to be attracted to the positive ends of the water where the hydrogens are. Right. So if we want to boil something, the interactions have to break because we're going from the liquid phase to the gas phase. All right, so if we just have water, then we're breaking hydrogen bonds primarily in order to undergo that phase change. All right, if we have water with salt dissolved in it, or anything dissolved in it really, those interactions must be more favorable than the interactions with just the water with itself. Okay, so what that means is this sodium ion, for example, or this sodium ion at the surface, is going to hold on to those water molecules a little bit, and the same thing with the chloride ions here. Okay, so if we heat it up, it's going to take a little bit more energy in order to allow those water molecules to escape into the gas phase. Okay, and so the boiling point will go up. This is called boiling point elevation, and it's because the interactions with the particles that are dissolved are stronger than the interactions of just the solvent molecules with themselves. All right, similar to that, we have freezing point. Okay, so in this case, we're going from the liquid phase to the solid phase. All right, so in order to form a solid, if we just have our normal sample of water, we need to maximize the interaction of those hydrogen bonds. Okay, so when we're in the liquid phase, some of those hydrogen bonds form, but we haven't reached the maximal number of them, and so the water molecules are still able to move around a little bit. Right? If we add in a solvent, or sorry, a solute of some sort, like we have with these green circles here, then we're now having other interactions with the water, okay, and they're going to get in the way of those hydrogen bonds that need to form in order to make a solid. Okay, so we actually have to cool it off more if we have something dissolved than if we don't have something dissolved, all right, and this is called freezing point depression. All right, so depending on what kind of thing we dissolve, the effect could be more or it could be less. Okay, so we have electrolytes shown here in these beakers, okay, and the water molecules aren't shown, but you should know that the water molecules that are in there are going to interact with the particles in each of these beakers, or else it wouldn't dissolve. All right, if we have a strong electrolyte, that would be like the sodium chloride I just showed you. When we put it into solution, it's going to form ions. All of the particles are going to break apart into their individual ions. So if it's something like sodium chloride, you'll get one positive ion and one negative ion for each particle that you dissolve, okay? But if it's something like calcium fluoride, that is CaF2, so you would actually get 3 particles for each of the ones you dissolve in that case, okay? Non-electrolytes, this would be things that don't break apart at all when we dissolve them. So the molecule the intermolecular forces will break, but the molecules themselves will stay together, right? And so based on what we've done before, strong electrolytes are going to be ionic compounds. Covalent compounds are going to be our non-electrolytes. They're not going to break apart, all right? And then there's this category in between, which we haven't really talked about a lot, weak electrolytes. So they break apart a little bit, all right? If we get to it at the end of the semester, we'll talk about acids and bases, and some of those are examples of weak electrolytes, but for your purposes, you just need to know that they're going to break apart a little bit. All right, and so the more particles we get when we dissolve something, if it's a strong electrolyte, the larger the effect it will have on the colligative properties.